Good afternoon, chemistry family. My name is Michelle Sanner. Today, we are going to be talking about the law of conservation of mass. So, by the end of today, you should be able to apply the law of conservation of mass to chemical reactions and see how the two of them relate. So, conservation of mass, simply put, is a law that states that in a chemical process, in a chemical reaction, atoms are not created, they're not destroyed, but rather they're rearranged. And they're rearranged by breaking and forming new bonds or rearranging bonds to create a new substance. Remember, it's only in nuclear reaction that the identity of the atom can be altered. But in these regular chemical processes or chemical reactions is another way of thinking about that, atoms can't be created. They don't spontaneously appear. They don't spontaneously disappear. They are always accounted for. And so today what we're going to learn is a little bit about how to make an accounting of those atoms in a chemical reaction. So let's look at the various features of a chemical reaction. Here is an example of a decomposition reaction. So let's label the reactants, the products, the phases in the reaction arrow. Our reactants are this original compound that reacts. It's always written to the left of the reaction arrow, and it indicates the substance that we have before the reaction takes place. Conversely, our products are at the end of a reaction. So and there could be multiple reactants, there could be multiple products, but in this case, it's a decomposition reaction, meaning there are this initial reactant is broken apart into multiple different substances by the time the reaction is done. So there's also another important thing here, the phases. So these phases of each substance are indicated in parentheses with lowercase letters right next to it. And so what this means is we start with something that's a solid, it reacts to form a compound that's a gas, another compound that is a solid, and another gas here. So we put the phases in parentheses with a lowercase, S for solid, G for gas, L for liquid. And the last component of our reaction is this reaction arrow. This reaction arrow shows the direction of the reaction. Usually it's pointing forward in the forward direction. And the way that we would speak this if we were trying to describe this chemical reaction is we would say that this yields or reacts to form or produces some compound. And then occasionally we may see reversible reactions in which you will have a double-headed arrow that indicates the reaction can proceed one way and then back again the other way, although that's less common. So phases, we talked about these phases. They are included in parentheticals right there next to the compound in question. Gas is with a lowercase g. Okay, we got to make sure that we don't use an uppercase here because the uppercase means something completely different. Or liquids are lowercase l's, and solids are, as you can imagine, lowercase s's. There's another phase of matter I'd like to tell you about today called an aqueous phase, and it's AQ in parentheses. So what this means is you have a substance that's been dissolved in water, like a solid that's been dissolved in water, but the water is not participating in the reaction. The water is just really the substrate or the mechanism for the reaction to take place in, but we don't write it in the chemical formula because none of its bonds are going to be broken or remade or rearranged in any way. So aqueous means dissolved in water, but the water does not participate in the reaction. All right, so chemical reaction. It's important that you understand chemical reactions are like a recipe that tells you exactly how many of each ingredient and in what ratio you need to form them. For example, if I asked you to go make cookies, chocolate chip cookies for me, and I simply said, you're going to use butter, sugar, eggs, flour, chocolate chips, baking soda, and go. Well, without specifying the quantity of each ingredient, you wouldn't be very unlikely to get good tasting cookies. You couldn't just add the same amount of each of those ingredients. You wouldn't want a cup of baking soda and a cup of butter and a cup of chocolate chips. It would taste pretty funky. So the chemical reaction ratio starts to become more and more important as you make those analogies to baking. Here's another analogy. Consider a bicycle, for example. A bicycle is composed of, let's oversimplify, 2 wheels and 1 frame, and yields 1 bicycle. And we couldn't just have one wheel and one frame. That would be a unicycle, something completely different than a bicycle. So using the ratio here in front of the substance, we call this a coefficient. Adding a coefficient in front of the substance tells us a little bit about the quantity that we will need of that substance in order to make this reaction go in the right way. So an important little star here is that unlike algebra, at any given time, you can only have either the reactants or the products, but not both. So what I mean by that is once I take the two wheels and one frame and combine them together to form a bicycle, they no longer exist as separate entities. We no longer have two wheels and one frame because we now have one bicycle. So another way of thinking of this is that all of the reactants are used up to create this product at the end of the reaction. So these two do not exist simultaneously, reactants and products. They are mutually exclusive. Once a reaction takes place, the reactants are gone and all that's left is products. So let's take another closer look at this chemical equation. So few different components here. We have subscripts. And as you recall, the subscripts are these small little down below numbers here that appear after the atomic symbol, and they count how many atoms form that particular molecule. So this nitrogen gas, for example, is formed by a bond between two nitrogen atoms. This chromium oxide here, we've got two chromiums and three oxygens would form this. And then over here, we've got water. H2O means that I have two hydrogens and an implied one oxygen. It should be reviewed at this point that if you don't see a subscript, the implication is that there is only one of that atom. So these numbers cannot be altered, okay? Because if you start to add and remove these numbers, you are changing the identity of the molecule. So don't touch those when we go to learn about balancing equations. Instead, you are going to use coefficients. And let me just show you what a coefficient is here. A coefficient is a large, and I mean large in size, like this one right here, large number before the molecular formula that tells you how many of that type of molecule you will need in order to make the reaction go. It's kind of like saying, you know, I need 4 cups of water here, or the ratio in your cookie recipe. I need a cup of butter and 3 cups of flour. And that's what a coefficient is like. Now you can adjust these numbers in order to make the law of conservation of mass become valid. And we'll do that in another video. But for today, just know that these large numbers that appear in front of the molecular formula refer to the number of molecules of that type that are required for reaction. And these numbers can be altered in order to balance the equation, a skill we'll learn about next time. So the subscripts, the small numbers down below, these are a count of how many atoms of each type we have. And the large coefficient out in front is a count of how many molecules are required to produce that reaction. So I suggest that students who are starting to learn conservation of mass and balancing chemical reactions begin the skill of taking an atomic inventory. And this is just a fancy way of saying count how many of each type of atom you have. We have to take into account the subscripts and the coefficients and any parentheses that may occur in the chemical formula. And so according to the law of conservation of mass, no matter should be created or destroyed in this reaction, which is to say you should have the same number of atoms of each kind before the reaction takes place as you have number of atoms of each kind after the reaction takes place. So we don't want any atoms to disappear. We don't want any atoms to come out of nowhere. We're just going to make sure that they have an even number before the reaction begins and afterwards. Because conservation of mass says that matter is not created or destroyed, but rather it's just rearranged. So we should have the same number of atoms simply rearranged if we're taking a correct atomic inventory. So let's do that. Here is that same reaction we've been working with today. We are going to take account of the atoms in the reactant side and the atoms in the product side over here. Okay, so I've broken down each different element that appears in this formula. So let's start with nitrogen here. I have nitrogen, Notice that it is followed by an implied 1 subscript, but notice that that entire compound is inside parentheses, and this little 2 over here means, hey, you actually have 2 of everything that's inside that parentheses. So instead of having 1 nitrogen, I actually have 2 nitrogen. So another way of writing this, NH4 2 is the same as an NH4 and another NH4. So I need to include 2 nitrogens there. For number of hydrogens, I have 4 hydrogens 2 times. So that would mean a total of 8 hydrogens for the same reason. Look, I have NH4 twice over. So NH4 and another NH4, making the total of my hydrogens come up to 8. Next atom in my inventory is chromium. Here it is. It looks like I have 2 little atoms of chromium here. So I'll write a 2 there. And lastly, in the oxygen subscript, I have 7. So for a total of 7 oxygen. So for the law of conservation of mass to be true, I expect that I should have the same number of atoms of each type of atom here in this column as well. So let's double check. Nitrogen. I see that I've created a gas of nitrogen that has 2 atoms of nitrogen in the molecule for a total of 2. I'll moving just across here, I have chromium with a 2 subscript, so that means 2 atoms of chromium. So far, so good. Over next door, I have oxygen, 3 oxygen atoms, but watch out, there's another oxygen over here. And here's what I mean about include any coefficients if needed. This 4H2O here is really like saying I've got an H2O, and another H2O, and a third H2O, and a fourth H2O. So I need to include all of those oxygens, 1, 2, 3, 4, plus the 3 from before for a total of 7. And look at that, it actually matches. So we'll do the same thing here with hydrogen. I have 2 hydrogen, but look, I have that 4 times. So really it's 2, 4, 6, 8 hydrogens. And if you've done the atomic inventory on a balanced chemical reaction, you should have the same number of atoms on the reactant side of each type as you do number of atoms on the product side of each type. And this demonstrates our law of conservation of mass, that atoms have not been created or destroyed during this chemical reaction. They've just been broken apart and rearranged in different ways, sort of like when you break apart and rearrange Legos. So let's do another practice problem. Take an atomic inventory of the products and the reactants of the following chemical equation. So I will go ahead and start by listing all of the different elements in my problem: carbon, sulfur, and oxygen. Over here on the reactant side, I have 1 carbon. So I'll just put a 1 there. For sulfur, I have 2 atoms of sulfur in this compound, so I'll put 2. And finally, for oxygen, I have a molecule. My molecule is O2, but I have 3 O2 molecules. So I have to take 3 times 2 is a total of 6. And I expect to find the same number of atoms on the product side. But let's double check. All right, starting from the left and just working right. I have 1 carbon. I don't see it anywhere else. I have 2 oxygen here. So I'm just going to put that 2 there and keep going. And then over here, I've got the coefficient of 2 surrounding that SO2 compound. So what that really means is I have SO2 and SO2 again. I have 2 molecules of SO2. So let's see, that means I have 2 total atoms of S, and then 4 more atoms of oxygen. So 2 and 4 add up to 6. So 1 balances with 1, 2 balances with 2 for sulfur, and for oxygen, I start with 6 atoms of oxygen, and I finish with 6 atoms of oxygen. So another atomic inventory. Now, I'd like you to try one on your own. So for this next practice problem, can you pause the video try to take an atomic inventory on your own. I'll do the same. And when we come back, we'll check your work and see how you did. Okay, so hopefully you were able to determine the number of products and reactants. I'll walk through it one more time for anyone who needs to see this again. So I'll just start from left to right. Looks like I've got 1 carbon in this first compound and 2 atoms of oxygen. So I'll just write a 2 there. I do see that there's more oxygen, but I'm just going to get to that one when I get to it, and I'll keep going here. And then it looks like I have the coefficient of 2 before the this molecule, LiOH. So what this is saying is I have everything after that 2 times. So lithium hydroxide, lithium hydroxide. So how many total atoms of lithium do I have? Well, I have 1 here and 1 here. So 2 atoms. I also have 2 more oxygens, 1, 2. So I'll add that to my oxygen count. And I have 2 hydrogens. So I'll add that there. So it looks like I have a total of 4 oxygens, 1 carbon, 2 lithiums, and 2 hydrogens. So if this is a valid chemical reaction, if this is a balanced chemical reaction, what I can expect to find is the same number of atoms on the reactant side. So let's see how we did. Over here, I've got 2 atoms of lithium in this compound, 1 atom of carbon, and 3 oxygens. So I'll just put 3 there. I know I'm going to have to add to that in a moment. I'm just going to keep moving to the right, and I see I've got 2 atoms of hydrogen and 1 final atom of oxygen. So 3 plus 1, again, equals 4. So I hope that you see that we are simply taking atoms and just like they were Lego pieces, breaking them apart, breaking them all apart, putting them all back together in a different way, but we still have the same number of Legos as we did when we start. In this case, we still have the same number of atoms as we did when we start. We've just broken them apart and rearranged them in different ways. That's all a chemical reaction really is the rearrangement of bonds. And so when we meet again, we are going to start practicing what happens when you have a chemical reaction that is not balanced, and how can you make it follow the law of conservation of mass by changing the coefficients out in front. So I hope you're doing well and that you're having a great day, and I'll see you next time.